Thanks for watching our talk. We will introduce the technology we use in REVERIE challenge. In this talk, there are two important parts, the navigator and the pointer. The navigator needs to find a way to the correct viewpoint, and the pointer grounding the object with the description of instruction. So we will talk the improvements in these two aspects. For navigator, we will talk about two strategies we use in this challenge, the distance-aware backtrack strategy and the endpoint decider strategy. The distance-aware backtrack strategy will reduce the search path of navigation, and the endpoint decider will increase the success rate of finding the correct viewpoint. And for pointer, we use ViLBERT to replace Magnet in baseline. We will introduce ViLBERT and how it works on this task, and then talk about the ensemble method of ViLBERT. Here is our method pipeline. The FASA navigator uses language instruction and panoramic image at each viewpoint to decide which is a nice viewpoint to go. Distance-aware backtrack strategy can reduce the search and backtrack length of FASA. The endpoint decider will help to locate the destination. Once the destination is decided, the ViLBERT pointer will use the image at the endpoint and make a prediction of the target viewpoint. So first, we will introduce the distance-aware backtrack strategy first. Before that, because our navigator is based on FASA model, we will introduce it briefly. In FASA model, there are two different scores for points generation process, the local score and the global score. When the model is generating trajectory, it will compute a local score for each reachable viewpoint. The local score represents the confidence of choosing the trajectory from the start viewpoint to this viewpoint. At each time step, it will go to the viewpoint with the highest logit, which is the local score, to extend the path. After path is generated, the model considers all viewpoints in its trajectory as a candidate of destination. It will use the local global score based on speaker machinism and progress monitor to evaluate the passes from the start one to any point in the trajectory, and select the point with the highest score as the final endpoint. But there is a weakness in this search strategy of us. We can see from the trajectory generation process. At viewpoint 1, the agent is very close to the end viewpoint. It can go to the viewpoint 2 directly and get the end of its journey. But viewpoint 3 has a higher low score, even though it's not higher a lot than viewpoint 2. The model goes to viewpoint 3. It is far away. This backtrack increases the trajectory length and is helpless to increase the navigation success rate. This phenomenon appears a lot in the navigation process of past. We can see from below. Why not make the model to consider the nearby viewpoint first? So we propose the distance-aware backtrack strategy. In this picture shows a trajectory generation time step of FASA. In this graph, the blue points are the points that have been navigated. The white one is where the agent now is. The orange one is the next candidate viewpoint. The green one is the target viewpoint. The dotted line between two nodes means the nodes are reachable on both sides. The logit value is predicted by the fast model as a local score. Based on the strategy fast, it will go to viewpoint 1. Because the logit value is higher, but it is useless for finding the target viewpoint and increases the navigation length. Even though viewpoint 1, the logit is 0.25 and viewpoint 2, the logit is 0.2, it's not higher a lot. So we use this logit to replace the origin logit, computed as shown above. W is a hyperparameter that influences the importance of distance in this logit. We take W equals 1 for example. And this logit for these two viewpoints is shown as above. If we use this logit to replace the logit before, the agent will go to viewpoint 2 directly. In this way, it will reduce the backtrack cost for navigation. Here are some of the experiment results of backtrack strategy. We can see our strategy is helpful to reduce the navigation length in both seen and unseen environments, and the effect is more significant in well-unseen environment. We can see from the third line, when W equals 1, navigation path cuts in half and the success rate keeps at the same level. Thus makes the RGS mercies increase. With the increase of W, the navigation length reduced from 32 to 14, and when W equals 2, get the best RGS result. Let's come back to the method pipeline. Next, we will introduce the unitary endpoint decider. The endpoint decider can locate the most possible destination of navigation. Decider is based on the unitary model. It is a large-scale pre-trained model for joint multimodal embedding. Unitary shows good performance on many different vision and language tasks. It is pre-trained on 3 big vision and language datasets, includes Cocoa Visual Genome, Capture No Captions. During training, it uses 4 self-supervised learning tasks. Includes masked language modeling, masked region modeling, word region alignment, and image text matching. We fine-tune unitary on the REVERIE dataset in order to get the matching score between region of interest and instruction. We use a multi-layer processor after image embedding output from the unitary. Because the multi-layer processor shares parameters across different image embeddings, in experiments, we find the score predicted from the unitary is comparable across different images, which means it can locate the most possible object from multiple viewpoints at a good accuracy. Based on this characteristic, we use unitary to evaluate and rank the viewpoints. The process is shown at right. For each viewpoint, the faster ASEAN will extract the region of interest features and feed them into the unitary model with instruction. The faster ASEAN is fine-tuned on visual genome. The matching score of different regions of interest is computed after multi-layer processor and summed region of interest score more than a threshold value that belongs to the same object. means that the object appears in this RI as its object score. We get the biggest object score in this viewpoint as this viewpoint score. And we use the viewpoint score to rank all viewpoints. The viewpoint with the highest score is the most possibly the endpoint of the navigation. In this page, we show the endpoint decider results. We take this experiment on well-unseen site. In baseline, the navigation success rate is 16.415, but if we use the endpoint decider, it increased to 29.79. It increased a lot. So it proves this method works. And come back to the master pipeline. It comes to the last part of our method, the multi-module fusion of ViLBERT. ViLBERT is a two-stream pre-trained model, and it shows state-of-art results in lots of vision and language tasks. Therefore, we adopt ViLBERT model that pre-trained with 12-in-1 training strategy to predict the target object at the ending viewpoint of each navigation path. To fine-tune our REVERIE, we pass the embedding of each image region into a learned linear layer to predict a matching score. Here is the structure of the ViLBERT pointer. We use a facet RCN to extract image features and feed these image features with instruction to ViLBERT and get embeddings. After the linear layer, a matching score is predicted. In one viewpoint, there might be many regions of interest of the same object. So we compute the score of an object by averaging the score of different RI that contains this object. That will increase the robustness of the RI score because there might be many different perspectives of this object. The average of the RIs means the finally performance of this object matching the instructions. And the one with the highest object score will be the target object. Because object can be seen in different perspectives, requires a robust pointer to predict the object described in the instruction. So we choose to ensemble ViLBERT on different training sites. We average the region of interest score from different ViLBERTs as an ensemble matching score, then use the ensemble score to rank the object in the viewpoint to get prediction. The ensemble matching score shows better performance on unseen environments. Here is some experiment results. In this table shows the referring success rate at the ground truth viewpoint. The ViLBERT success outperforms the MANET a lot. Under different training set, the ViLBERT is about 16.4, but the MANET is about 56. And then we do experiments on the predicted endpoint of navigation by fast. We can see that if we use single ViLBERT, it outperforms the MANET in baseline. And if we use the ensemble ViLBERT, it outperforms the single ViLBERT. It shows that our ensemble method works on this task. And if we combine all the best results in pointer and navigator, we get the final result on unseen environment. It outperforms the baseline a lot. So much for our talk. Thank you.